Hi, my name is Mohammad Naseri, a PhD student at University College London. I'm going to present our work Local and Central Differential Privacy for Robustness and Privacy in Federated Learning. This is a joint work with Jamie Hayes and my advisor Emiliano di Cristofaro. In centralized machine learning, training data is centralized, and we train our model on that data, and then deploy our model. However, there are different limitations like data collection, storage capacity, and privacy for centralized data. Federated learning is an emerging machine learning paradigm to address the challenges of the centralized machine learning. It is a setting where multiple clients or participants collaborate in solving a machine learning problem under the coordination of a central server. Each client's data is stored locally and not exchanged or transferred. Instead, model updates intended for immediate aggregation are used to achieve the learning objective. So the motivation would be the number of clients, meaning more data and better model, and privacy, in a way that there is no direct access to the participants' data. A widely used framework that we also focus on this paper is federated averaging. Differential privacy has the following definition. A randomized mechanism M provides epsilon delta differential privacy if for any two neighboring databases D1 and D2 that differ in only a single record and for all possible outputs S, the probability that we see A when the dataset is D1 is at most e to the epsilon times the probability that we see A when the dataset is D2 plus delta. Epsilon is known as the privacy budget, and delta accounts for the probability on which the upper bound epsilon doesn't hold. We have different variants of differential privacy in federated learning. In this project, we mainly focus on local and central differential privacy. Local differential privacy is also known as record-level differential privacy, and central differential privacy is also known as participant-level differential privacy. The way that we implement them is that in local differential privacy, each participant trains the model that is received from the server on its dataset using DPSGD. In central differential privacy, the server is responsible to aggregate the model updates from the participants in a differentially private way. More specifically, in local differential privacy, every participant trains the model using DPSGD. In DPSGD, the sensitivity of each gradient is bounded by clipping the gradients and afterwards sampling random noise and adding it to the clipped gradients. In central differential privacy, the server bounds the updates from participants by some value and then it adds some amount of noise using like a normal or Gaussian distribution. We categorize the attacks in federated learning to poisoning and inference attacks. Poisoning attacks, which they also target the robustness, the adversary tries to reduce accuracy of the model or make it misbehave on specific inputs. We focus on backdoor attacks in this project. So in backdoor attacks, the backdoor attacks or targeted model poisoning attacks where a malicious client injects a backdoor task into the final model. And inference attacks, which they target the privacy, we focus on membership and property inference attacks. So in membership inference attacks, the goal is to determine if a specific data point was used to train a model, and in property inference attack, the goal is to recognize patterns within a model to reveal some property which the model producer might not want to disclose. So in backdoor attacks, the attacker modifies its training dataset to introduce backdoors into the global model. Backdoor attacks are easy to implement and quite effective. It is difficult to control the local model submitted by malicious participants, and defenses that require access to the training data are not applicable, as that would violate privacy of the participants, defeating one of the main reasons to use federated learning in the first place. Some defenses require inverting the model to extract the training data, which doesn't work because of the same reason. We focus on the two existing defenses by Sun et al., norm bounding and weak differential privacy. They do not provide privacy, but just robustness against backdoor attacks. The reason that they do not provide privacy is that in norm bounding, server can ensure that norms of participants' updates are within the threshold. However, updates can still leak information about the training data. And in weak differential privacy, we have norm bounding plus adding Gaussian noise. However, since we have a composition theorem in differential privacy, all those epsilon values will add up and result in a large final epsilon value, which doesn't provide privacy. For membership inference attacks, we focus on the attack proposed by Naseri et al. The main intuition is that each training data point affects the gradients of the loss function in a recognizable way. So for instance, in this example, which is like a classification task, we have this curve, and then there is a new data point. It performs a gradient descent to include that in the correct class. Then if it goes further, it tries to correct that again, and at the end we have the correct classification there. However, if there is a new data point which doesn't belong to the blue class, nothing would happen. So the attacker can perform gradient ascent on a target data point before updating local parameters. So for instance here, it performs gradient ascent, but since this is a member of the training data set, nothing would happen to the curve. And for a data point which is not a member, we'll see a change to the curve. And then we also have active and passive, global and local, depending on like if the server or participant performs the attack. For the property inference attack, we focus on the attack proposed by Melis et al. So the attacker's goal is to infer the properties of the other participants' datasets. At each round, the participant's contribution is based on a batch of their local training data, so the attacker can infer properties that characterize the target's dataset. To do so, the adversary needs some auxiliary training data, which is labeled with the property that the adversary wants to infer. For the defenses against inference attacks, the main problem is the information leakage from the aggregated model updates. There are defenses like dropout or gradient sampling, so that the adversary observes fewer gradients. However, these approaches only slightly reduce the effectiveness of the inference attacks. There are prior works aiming to mitigate membership inference attacks in black box setting, but not in white box or federated learning setting. So the main motivation is that can we have both robustness and privacy in federated learning? As there are no defenses against both privacy and robustness attacks, more specifically against the explained attacks. Differential privacy is supposed to mitigate inference attacks, especially membership inference attack, but there are no experiments in FO. So for our backdoor experiments, we focus on EMNIST, C410, Reddit comments, and Sentiment 140 datasets. In EMNIST, the backdoor is to change the color of the bottom right pixel and label it as 0. In C410, the backdoor would be to label all red cars as cats. In Reddit comments dataset, the attacker predicts sentences that include the city London with preset words as the backdoor. And in Sentiment 140, the attacker injects a backdoor text in the training data to make the aggregated model classify tweets with the backdoor text as negative. We consider two settings for our experiments. Setting 1, we reproduce the setting considered by Sun et al. In order to have a fair comparison. And in setting 2, we consider an increasing fraction of malicious participants, aiming to show how effective defenses are against varying number of attackers. We compute both the main task and backdoor accuracies. We apply norm bounding, weak DP, LDP, and CDP. Here we can observe the results for EMNIST and CFAR10. The results show that both LDP and CDP with different epsilon values defend against the backdoor attack, although decreasing the utility. However, they are more effective than norm bounding and weak DP. For setting 2, we can see the results for EMNIST. We can see that the effectiveness of varying the number of attackers here, and one interesting thing here is that in LDP, if attackers opt out of applying differential privacy, then the attack would be boosted. So the takeaways would be that LDP and CDP can indeed mitigate the backdoor attack, although they do with different robustness versus utility trade-offs. Weak DP and norm bounding mitigate the attack without really affecting the utility. In both settings, LDP and CDP are more effective than norm bounding and weak DP, although with varying levels of utility. And in overall, CDP works better as it better mitigates the attack and yields better utility. However, CDP requires trust in the central server. The same values for epsilon in CDP and LDP do not imply that they provide the same level of privacy. And for larger datasets like Reddit comments, utility loss was less compared to other datasets. For membership inference attack, we considered CFAR 100, Purchase 100, and Texas 100 datasets. We consider 4 participants, and we measure attack accuracy as the fraction of correct membership predictions for unknown data points. We observed that both LDP and CDP mitigate the attack, considering that the baseline attack is a random guess with 50% accuracy. For property inference attack, record level differential privacy is not meant to defend against the attack, and we can see that in our experiments. CDP is meant to defend against the attack, however, with experimented epsilon values that the model converged, the attack was not mitigated. So the takeaways would be that LDP and CDP can defend against white box membership inference attacks in federated learning without destroying utility, and neither LDP nor CDP successfully defend against the property inference attack with the experimented privacy budgets. Thank you.